Okay, let's just get back to it. So we've seen some of the and stuff like that. I want to give you 2 more examples of group actions. Well, like the examples I gave before, you might think of them as being like, I don't know, like group actions in the wild or something like. And this is more of like what can also happen is that a group can act on itself as well. Let me show you what I mean. Okay, so define. So let me be careful. Okay, let X equals G, and let G act on itself by alpha gx equals G times X. Okay. So this group action, is called translation. Okay. And then as a generalization of this, you can let H be a subgroup of G and let X be the cosets of H, the left cosets, then define. So then G can act on the left cosets by, again, left translation. Okay. So that's like one thing that can happen. We also get a group action if we look at conjugation. Let's see that. Another example. So again, let G be a group and X also is equal to G, then define alpha from G. Let me rewrite this. Alpha of Gx just to be Gx G inverse. This is conjugation. This is the action of conjugation on G. Okay, and then as a generalization of this, yeah, one more example. Let X be the set of all subgroups. And define alpha GH just to be GH G inverse. Okay. So the group G can act on all the subgroups of G by conjugation. So this action is also called conjugation. Okay. Okay. So whenever we have a group action, so we like to look at the orbits and the stabilizers and so on. So actually these two things are related. This is called the orbit stabilizer theorem. Okay, and this theorem says, so a G act on a set X. Okay. Let X be an element of the set. Then what happens is that the index of the stabilizer in G is equal to the size of the orbit of X. As long as, I mean, this only makes sense if these are two finite numbers. So as long as either this index is finite or this is finite. Okay. If they're both infinite, then that's fine too. But as long as one or the other is finite, they're both finite and equal. Okay. Okay, so for this proof, I'm actually going to skip a lot of the details and just give you the main idea, just so we can state our other main property about group actions today. Okay. So the idea is you construct a bijection between the left cosets of the stabilizer and the elements of the orbit. So you construct, let's call it phi, from G mod Gx to the orbit of X by putting, I'll take the coset of H and define that to just be Hx. Okay. So this gives you a natural way to each left coset of the stabilizer, you associate an element with the orbit. And then what you have to do, which I won't do, but you know, the way forward is, I guess, clear. You have to check the following. You have to check that phi is well defined, meaning I've defined a function on the set of left cosets, but I've defined it in terms of this representative of the left coset. So I need to check that phi of H Gx equals phi of H prime Gx if H and H prime are in the, if HGX equals H prime GX. I need to check that phi is well defined. Then I need to check that phi is 1-to-1 and onto. Okay. Once I do that, then I have a well-defined, like a bijection between this set and this set. So if they're, either one is finite, they both have to have the same number of elements. Okay, and then after you do these two things, you're done. Okay. But if you kind of remember what construction to use, these steps are kind of like just like checking off boxes. They're pretty straightforward. Okay. Okay. So we have the orbit stabilizer theorem. So it tells you if I tell you how many things are in the orbit, you also know how big the stabilizer, like how many elements fix X. Okay. And well, for me, the reason that this theorem is important is because you use it to prove another theorem called the class equation. Okay. So if I have a chance to go through that, I will now. So let's see. So you have a definition. Let G be a group acting on X. Okay. Then we define the center. Denoted Z by the rule. Z is those elements of X such that Gx equals X for all X, or for all G, sorry. So in other words, if Gx equals X for all G, that means the orbit of X has one element itself. So Z is like the union of all the orbits which have one element. So the theorem, which tells us, which is the class equation, the theorem is that the orbits of X under G give a partition of X. Okay. Equivalently, if you can define an equivalence relation on X. Define for xy in X, X tilde y, if and only if Gx equals Y for some G, then this defines an equivalence relation on X, okay? And the equivalence classes are just the orbits, okay? Now equivalence relations give partitions, so that's why orbits give partitions. Okay, and then what this implies is that, so 3, you get the theorem that the number of elements of X is equal to the number of elements of the center plus a summation what's the summation? Summation of the index, the summation over, like basically when we want to take the summation over all the non-trivial orbits. So where A is a set of representatives of the non-trivial orbits. Because all the orbits of size 1 are here, so all the orbits of size bigger than 1 are here. Okay, and the idea of this theorem is that once you show that you get this equivalence relation defined by the action of G, I'm just going to draw a picture for this. But I believe I did write it down in the notes if you want to see. Okay, so once you partition X into all the different parts, here's the center. This is another orbit. This is another orbit. And so on. This is a partition. Well, the orbit stabilizer theorem says that the size of this orbit has this many. The size of this orbit has this many. And so on. Well, the number of elements here is just that. Okay. Now, since we have a partition, this is the picture of X. To find all the other, to find the number of elements of X, we just add up the number of elements in Z, the number of elements in this partition, plus the number of elements in this partition, and so on. And we just have to pick out, well, we just have to add all the elements in the center, and we just have to pick out one representative from each orbit. Okay. And once we do that, we get this sum. Okay. So right. So I think I'm gonna stop there, and then today I'm going to upload. So here is what you should expect. What for me to do, look out for solutions to assignment number 2 and just a video on examples of the class equation. And then assignment 3. And assignment 3 will just all be about these things we've been talking about today and also on Monday. Okay. So let's just stop there. Oh, how much time are we getting to do the coursework? I have to get back to you on that for the exact timing. Yeah, but I didn't forget. I will get back to you as soon as possible. Well, yeah, maybe not today, maybe early next week. Okay. Any other questions about the coursework? Okay. Okay, well, I guess that's it. Well, thank you guys for watching and coming out. Guess I'll see you guys next week. Okay.